welcome everyone. I'm excited for our presenter this week coming from Middlebury. We have Sean Peters here, our only geologist this year, or I should say volcanologist, and I feel like that's really all I have to say, because that is exciting enough. So please join me in welcoming Dr. Peters.
Thank you, Emily. Let me see, does this, okay, yeah. I can project, it's fine. So hi, I'm Sean Peters. Today I'm going to talk to you about From the Lab to Mars, applying physical volcanology to extraterrestrial surfaces. So for starters here, this is a beautiful image from the Snake River Plain in southern Idaho. This is a lava flow. So this is was once a very volcanically active region, and thanks to the Yellowstone hotspot, the hotspot that's now beneath Yellowstone. So we're going to dive a little bit into physical volcanology, aka just geology, and then how we use that to explore extraterrestrial surfaces, the surfaces of other planets. So first off, who and what am I? I am an experimental volcanologist and a planetary, I specialize in experimental volcanology and planetary geomorphology. I'm a volcanologist and planetary scientist, so I'm a geologist by training. Specialized in volcanoes, right? So doing field work in Iceland and Hawaii and Mexico and places like that. And I'm also a planetary geologist. I spend a lot of time thinking about Mars and the moon and other planets and looking at those surfaces. So I'll talk a little bit about that. But also, I was born and raised in Mississippi, went to grad school and lived in Arizona for a while, where I fell in love with the sun in a powerful way. I then, after graduate school, I moved to Japan for a year and taught English before moving here to Vermont. My hobbies are like writing and traveling and food. I am also a human, not just a scientist. So I like Legos, I like food, I like binging TV shows, I like traveling. I like to think about how to facilitate inclusive, accessible, and equitable learning environments. That's something I really care about in the sciences, is making sure that we have all the people who want to do science doing science. Really good at writing and planning and big picture ideas, which is a big part of being a faculty member and doing research. And I'm working to improve giving grace to myself and others. So I, like all humans, we are dynamic and complex. I'm a work in progress, so there are things that I continue to strive to improve upon as well. My academic journey, what does it look like? For everyone, it looks totally different. My major in college, my bachelor's degree is in psychology, actually. My minor is in geosciences. But then I went to graduate school and got a master's and a PhD at Arizona State in geological sciences before I did a postdoctoral fellowship at the University of Idaho, and now I'm currently a postdoctoral fellow and faculty member at Middlebury. But in between that time, I took a year off and taught English in Japan, which was really, really awesome, and had a chance to step into the classroom with a totally different hat on and learn how to subsist alone in another country where I did speak the language, that's fine, but still, it was very, very different. So what I like to think about as a scientist is I like to think about big picture science. So I like to think a lot about regional and global volcanic observations. This image back here in the background is an inflated lava flow from Iceland. So I like to think a lot about volcanoes in different regions and different places. I like to think about comparative planetology. I like to compare planets, right? Why does the moon look weird? Why do the moon and Mercury look so similar? Why does Venus look absolutely bananas? Why does Mars look kind of familiar but kind of weird? I also like to think about volcano and surface evolution. Okay, we're going to talk about that a little bit later. Most of the surface of the Earth and most of the surface of every single planet in the solar system is covered in volcanoes. Why? How? What? Right? I like to think about different volcanic landforms, lava flows, things like that, shield volcanoes, channels. But I also like to think about communicating science with the scientific community as well as the public, also. Your tax dollars pay for this, right? So you should have access to this data. You should know what's going on. It's really important. You're spending half a penny on a dollar you give to NASA. So that's things that you want to be aware of. So the structure of this talk is going to be half physical and experimental volcanology. I'm not going to get super into the weeds and things like that. I really just kind of want to introduce the discipline a little bit. And then we're going to jump off into extraterrestrial surfaces and just look at some really cool planetary data. Because that's what we always like to look at. And in the background is another one of these big, thick lava flows from Idaho. So first, let's start off with physical volcanology. This is the Krafla lava flow in Iceland that was erupted about 30, 40 years ago. Iceland would highly recommend. If you want a spiritual experience, just go to Iceland. You see absolute raw, unaltered, mostly nature, amazing mountains and volcanoes. It's truly a beautiful country. So this picture I took last summer. So first off, I want to start with, why do volcanoes exist? Okay, so why do volcanoes exist? This is an example. This is a picture of Tahoma, aka Mount Rainier, in Seattle, Washington. So why do volcanoes exist? Is someone brave enough to yell out why they think they exist? Is it divine retribution, or is it, happenstance? Yes.
Tectonic plate movement and the creation of land?
Nerd! Yep, that's right. That's true. That is the correct scientific answer for sure, right? So it has to do with tectonics. It has to do with nature for sure. Why Seattle sits at this location boggles my mind, but it doesn't matter. Mount Tahoma was there before the city. It exists because, just like you said, there's something going on inside of the Earth's interior, right, that leads to tectonics. So the reason volcanoes exist is a function of the Earth's interior, right? Is the Earth's interior solid or liquid? So we know that the outer core is liquid, but everything else in the Earth is solid, asterisk, right? So the mantle is solid, the inner core is solid, squishy, according to the new science, but it's still solid. The mantle is solid. The Earth is really hot on the inside, okay? And so the reason volcanoes exist is quite simple. The Earth needs to sweat. It has to get rid of all of this heat. This is why volcanoes exist on every single solid body in the solar system. Even the ones made of ice have volcanism. Pluto has volcanism, right? It doesn't matter if it's ice or if it's silicate rock, they exist because of this internal heat. And this heat is a product of the formation of the planet, as well as the radioactive elements that are within the planet, okay? So that's why they exist. There's heat and it needs to get out of the planet. And it correlates with plate tectonics, right? And so our planet happens to be nice enough to have the surface crust broken apart into about 20 plates. And that happens to be where we see most of our earthquakes and where we see most of our volcanoes, right? So there is definitely a huge correlation there. But ultimately, the planet just has to sweat. This internal heat has to get to the surface, right? And so right off the bat, you can see that there is a correlation between these plate boundaries and where the volcanoes are. But you can also see that most of our volcanoes are not on land. They're mostly underwater, okay? So every now and then you'll see something in the news, including recently, because we have volcanic eruptions that are volcanoes are starting to rumble in Iceland as well as Mauna Loa. Every now and then you'll see people get in the news or on social media and go, oh my gosh, are there more volcanic eruptions happening? At any given time, there are 50 to 60 volcanoes erupting globally, subaerially, that we can see. There are always volcanoes erupting underneath the ocean, 100% of the time, all the time. They have to be, because that's why the plates are moving, right? So volcanoes are essential to our geology, to our planet's evolution, to our planetary history, and they're everywhere, right? And we can see them. Mostly we care about the ones that are erupting on land. The ones underwater we don't care about so much unless you're AT&T or a telecommunications company with your transoceanic cables, then you do care about volcanoes erupting underneath the ocean, because those cables have to go over those volcanic ridges. So in summary, that's just a very brief introduction of the fundamental mechanisms of planets to lose heat is through volcanoes. 90% of volcanism on the Earth occurs under the oceans. Volcanism has occurred on every solid surface body in the solar system. And volcanoes tell us a lot about the composition of a planet, its interior, and things like that. Its evolution, and it provides clues to habitability as well. And so we'll think about that a little bit more when we get into the planetary stuff. For me, though, what I decided to do is I like to use experimental volcanology to study lava, okay? So I want to go into the lab and I want to simulate some of these processes using different materials within the lab. And this is stuff that I did in graduate school when I was at Arizona State and continued to work on as a postdoc. So in the background here, this is a wax flow. This is polyethylene glycol wax. which is in some of your food and medicines and things like that. So it's technically edible. It's what keeps candy bars solid on grocery store shelves so that they don't, even if it's like 80 degrees outside. But you can also erupt this wax underwater, and it does a really good job of simulating lava flow dynamics and simulating the crust that lava flows form when they're erupted onto the surface. So I want to give an example of, so what does that look like? This is what lava looks like, right? Basaltic lava like we see in Iceland, all right? So this is an example of what we call Pahoehoe lava, okay? And so you can see it's really, really hot in the interior. It forms a crust almost immediately. This is very glassy, right? This stuff right here, you do not want to fall on. You don't want to do a push-up on it. It's really, really sharp. But this is how lava flows when it's very quiescent, when it's flowing at a very low rate in Hawaii. But it can also flow like this. So this is from the United States Geological Survey from an eruption in 2018 in Kilauea. If it flows really fast, you can get things like this, right? So here's a lava channel up in Kilauea. We have our vent where this lava's bubbling and erupting out of the earth. And then because it's erupting at a very high flow rate, you get these channels, right? And so these landforms can look a lot like what we see with river channels and things like that. Again, this is molten material flowing out of the earth. Lava is very difficult, of course, relative to water because it has solids and gas and all this stuff. It's a multi-phase fluid. But this is hot stuff. It's somewhere around 1100 degrees Celsius when it comes out, aka 2500 degrees Fahrenheit. And there's all this gas and stuff coming out of it. But the nice thing about lava flows is they're relatively safe. As long as you're like not right here, you can send drones up. If you're in Iceland, you can get really close to these. If you're in Hawaii, you can get close to them also. Because once they're away from the vent, they really slow down. But you can see we have this huge channel. All of this is lava, and everything that's black and brown, that's more solidified lava that's coming out of this channel, all right? So this is the kind of stuff that I like to simulate in the laboratory because A, I don't want to go out there, but then B, it's really, you can exert more controls in the lab. But this is an example of lava though. These are what we call effusive eruptions. They're not explosive. They're relatively quiescent. This is what happens mostly in the Galapagos, Hawaii, Iceland, places like that. Have our little cone, we have our lava flows. But most of you might be familiar with explosive volcanic eruptions. And so this is in Papua New Guinea 2014. And explosive eruptions can look a little something like this. This one just kind of shows what it looks like when you have these really powerful explosive eruptions. But basically there's two types of volcanic eruptions broadly. There's lava flows, which are a little bit more fluid, and then there's explosive eruptions when we think about Mount St. Helens and things like that. So apologies for YouTube being itself whenever there's a PowerPoint. Okay, so in summary, fundamental mechanism of heat loss, evolution of the planet. I use experimental volcanology in order to study lava flows. That's what I like to do. And so what makes lava flows so complicated? It looked pretty straightforward in that video. You had a lava channel look kind of like a river. Well, what makes it complicated is there's all these other factors that are impacting a lava flow propagation. So there's what's happening at the vent, right? That you saw that lava flow kind of bubbling out of that little vent mountain, kind of thing. The vent, what's the eruption rate coming out of that vent? How's the geometry of the vent changing? That can affect your lava flow. Exsolution of gases. There's all these different gases and volatiles inside of our magma. Most of it's water and carbon dioxide, but there's some sulfur dioxide too and other things like that. Then we have to worry about a crust. You saw the crust forming on that lava flow as it propagated towards the camera. Turns out that can have a huge impact on what happens with our flow as well, the thickness of that crust, how fast it solidifies. There's levees, just like a river. There's levees and overspills, right? So we're losing some mass to the construction of these levees. These lava channels, for example, in this image, these are constructional features, right? They're building the topography in this instance. And so we have levees and overspills. The viscosity is also changing. So viscosity is simply the resistance to flow. And a way that you want to think about viscosity, because it's so critical to when we're thinking about lava flows or any fluid basically that's not water, right, is viscosity is a fluid's resistance to flow. So water has a very low viscosity. If you tip over a glass of water, spills everywhere, gets everywhere, causes all kinds of problems, right? Water has a very low viscosity. It's Newtonian is what we would say, named after Isaac Newton. Has a very low viscosity. Motor oil has a slightly higher viscosity. So if you spill motor oil, it still goes everywhere, but it doesn't flow quite as fast as water. All right? Has a slightly higher viscosity, a slightly higher resistance to flow. Peanut butter has a very high viscosity, okay? If I plop down a glob of peanut butter, it ain't going nowhere, okay? And the only way you're gonna get it to flow is if you take a knife and you spread it, right? You have to overcome a yield strength. Lava behaves a lot like peanut butter, right? It does not, if you just put a blob of lava in the middle of this floor, it's gonna first set the carpet on fire, but then B, it's not gonna really go anywhere. It's just gonna sit there like a blob and kind of deform a little bit. So something must be spreading it like peanut butter, right? It's the force of it erupting out of that vent. That's what's controlling it. It's just the actual push, the force of it being ejected out of the earth for a variety of reasons at the vent, right? So lava has a high viscosity. It has a resistance to flow. It's not like water. And then slope. Topography is another thing that affects our lava flows. So when we're thinking about lava flows, one of the reasons I care so much about this is because it's really still hard to predict where they're going to go. It looks pretty straightforward, and it is if there's a steep slope, but sometimes it's not quite so straightforward. So for example, if I have a lava flow that's flowing from the upper left to the bottom right, and my topography is not steep, I'm on a relatively flat surface, I don't know where my lava flow is actually going to go. Right? So we have our lava flow here with our levees and our like molten channel like you saw in that video earlier. I don't know. Is it going to go towards Vermont State? I don't know, right? It's really hard to tell. There could be a breakout and it could head this direction. Is it going to threaten our puppy, right? I don't know. I hope not. This is my family puppy, so. So is it going to threaten our puppy? I don't know. Maybe we want to know if we live in town A or town B, which direction this is going to flow in, right? Or maybe it's going to flow towards your ex, in which case you don't care, right? So town C, we're not too worried about it, all right? So, but again, it's really hard to say. It's very hard to say when you're emergency management officials or if you're doing something like that. If your lava flow is not on a steep slope, it's very hard to predict exactly where it's going to go. That's what they're dealing with right now in Iceland. That's what they may be dealing with in Mauna Loa in a couple of weeks if it continues to erupt. If that lava is not going down the steepest slope, it's very hard to determine where it's going to go. So for my experiments, one thing that I wanted to think about was whenever you go in the lab, you want to control as many things as possible and you want to simplify nature as much as possible because nature's complex. So in a lab, I think about, does the lava flow thicken? Whoop, or does it expand? Whoop, because if it's expanding, then it might be a hazard for our community. If it's thickening, maybe not so much. It's not really growing in area. It's just thickening, okay? And so the way that lava flows thicken is through a couple of different ways. They can resurface themselves, stack on top of itself. It can inflate, it can endogenically grow, and I'll show examples of this in just a minute. Or it can expand, right? That's how it can thicken. Or it can expand. It can expand by breaking out at the margins, expanding. Or you can get lava tubes, which can transport material to the margin. And so we'll look at that. So that looks like this. So here's some examples, right, of breakouts, inflation in tubes. So here's what a breakout looks like, a surface breakout when I'm resurfacing. This is a lava flow that's active and it's just kind of breaking out on the surface and resurfacing itself, right? So it's not really growing in area. It's just kind of resurfacing itself. And so on our Louvre-worthy schematic here, what that looks like is I can have marginal breakouts, but I can have resurfacing, which is on the interior, right? So I have these intraflow surface breakouts, like in this image here, where the flow's not expanding, it's thickening, right? Or I can get marginal breakouts. That's going to extend my flow, right? That's going to be my hazard. I got to worry about that. That's going to affect maybe town A, maybe town B, or something like that. Another example is inflation. Lava flows can inflate. And so one way to think about that is here's a lava flow inflating. So this is what lava flow, this is Hawaii, and look across 4 hours. The lava flow propagates forward, but then it thickens dramatically, okay? So this is the Pahoehoe lava flow in Hawaii. Note how much it thickens as it comes towards the camera. All right. And even after it's propagated, it continues to thicken, okay? Lava flows can inflate. This is endogenic growth. This is material, like blowing up a balloon. This is material, molten lava being ejected underneath that crust that can thicken these lava flows. An inflated lava flow can go from being anywhere from about 30 centimeters thick to up to 30 meters thick, all right? These things can be absolutely enormous. If you go into the Columbia River basalts in like Washington and Oregon, you can see flows that are up to 50 meters thick because you just had magma constantly being ejected beneath this crust. And that can add up over time because then you can get large igneous provinces like this. So this is not the Columbia River basalt, but it looks very similar. These are the Deccan traps in India, in Western India, okay? And so all you see there are stacks and stacks and stacks and stacks of lava flows, right? And these lava flows are thick, 10, 20, 30, 40 meters thick. The Deccan traps were such a voluminous outpouring of lava that they are thought to have been a 1-2 punch that drove the dinosaurs extinct. You had the asteroid, but you've also had this going on for hundreds of thousands of years before the asteroid, which had already started to cripple the Earth's ecosystem, right? This is a lot of lava pouring out over hundreds of thousands of years. That's a lot of gas. That's a lot of stuff going into the atmosphere, a lot of ash and stuff like that. So inflation might be a really important process. We also want to think about lava tubes, right? So here's an example of a lava tube. Okay, yeah, they're cute. Lava tubes are great though because they are an efficient way to transport lava really long distances and keep it really, really hot. I know, well, some of you may have seen the movie Volcano from the 90s. And so there's a scene where they have lava going through a subway tunnel in Los Angeles because it makes no sense, but whatever. But you have lava going through the subway tunnel and the lava stays incandescent in the movie. That's what really happens in lava tubes, okay? And you can get lava tubes formed in a couple different ways. You can have a lava channel like we saw earlier. You can form some levees like we saw earlier, and then you can crust over it. And that's how you get a lava tube. Or you can have our flow like I just showed you, our little Pahoehoe inflated flow, and you can have pockets of hot material within there that become connected together to these preferred pathways, and you can form tubes that way. Fine, okay, we can get tubes two different ways. The most important aspect is that this is a very efficient way to transport really hot material really far distances, okay? And we can make them in the lab, right? With these wax flows, we can get these tube-like structures in the wax. We can get them forming under both of these conditions, which is really cool. So we are able to simulate some of these natural processes in the lab with this peg wax, okay? So that's an example of some of the things that we want to look at, ways in which a lava flow can expand and ways in which a lava flow can thicken, right? So what does our methodology look like? Again, another one of these beautiful wax flows. Without getting into too much detail, I will say this. Whenever you go in the lab and you have to do experiments, you have to use dimensionless numbers, right? These are numbers that have no units, right? And we have to do that because we have to make sure we're comparing apples to apples, which is a phrase I hate because you can totally compare fruits that are different from each other, but whatever. In science, we want to compare apples to apples. So we want to make sure that if we are looking at a flow in the laboratory, it's behaving under conditions that are similar to what we see in nature. So one of the dimensionless numbers we use is a number called psi. And all psi does is it relates the morphology, the way the lava flow looks, to the cooling conditions, right? And we can use it as a proxy for crust. So if I have a high psi value, I have a very weak crust, or I have a very fast propagating lava flow. If I have a low psi value, I have a very strong crust, or I have a very slow propagating lava flow. So earlier, when you looked at the inflated flow, those Pahoehoe flows, that was a high psi value environment. It had a very thick crust. It was able to inflate. When I look at my levees, my channelized lava flow, like we saw in that really cool video where it was erupting and it looked like a river channel, that's a high psi value, has a very weak crust. It's propagating very quickly. So we can use psi, this dimensionless number, as a proxy for crust. And again, this is important because now I can apply psi values to the flows I see in the lab, but I can also apply it to flows that I see in nature too. And I can know that I'm looking at similar conditions because it has no units. It is dimensionless, right? It's just the time scale for the crust to solidify to the time scale of lateral propagation, roughly, okay? So the way we do that is we just go in the lab, have a little rinky-dink tank here. We've been using this tank for 30 or 40 years. It's pretty great. Ideally, what you have here is a tank. You fill it with water. You put a camera over it. You have a programmable pump. You can have wax of different colors in different reservoirs, depending on how many eruptions you want to do. And then you erupt it in the lab, and it looks something like this, right? So this is an example of a multi-stage eruption. That's the first stage. Second stage, we get a marginal breakout here. and some resurfacing going on. And in the third stage, we have a lot of resurfacing and another breakout. I've sped this up dramatically. This experiment was really like 5 minutes. So let's look at it again. It looks like this, right? So boom, you have this lava flow erupt. And then in the second stage of the eruption, you have these outbreaks and this resurfacing. So you can see our flow is expanding, but it's a thickening in some areas. And then you have this final breakout in stage 3 where you see some resurfacing as well as expansion, right? So we saw a couple of those different processes that we looked at earlier. We saw resurfacing where this wax resurfaced each other. We saw marginal breakouts where the flow expanded, okay? So we can go in the lab and we can test these things out and get an idea for the dynamics that's going on. So results, I'm not going to throw a bunch of quantitative data at you. You can go read the paper if you want to waste a Saturday and future papers. So here's an example of one of these flows again. But what it can look like is something like this. So basically what I can have is I can produce these different flows under different psi or crust conditions. So I have flows down here. See, this one here looks very thick and bulbous. It has a low psi value. It has a strong crust. It's inflated. That's why it looks like that. These flows have not inflated at all. They have a very weak crust. They've expanded. So now I kind of see that, hey, my thickening conditions tend to be down here. My expanding conditions tend to be here, right? And I can even vary the pulse. I can vary how much I'm changing the eruption rates and the lengths of time. And I can get different morphologies based off of that, right? So, yeah.
How many eruptions do you have going off at once in these experiments?
Oh, one. Yeah. There might be different stages though. So that experiment, that video that I showed you had 3 different stages, but it's all the same eruption. So yeah, but it's all one experiment at a time. But I ran like 600 of them, so it took a lot of time. But yeah, but one at a time. But you can have as many stages as you want in your eruption. You can just erupt one stage of material at some given eruption rate. You can erupt 2 or 3 stages if you want to simulate different eruption rate patterns and things like that, for sure. So you can really turn these parameters as much as you want. In the case of my experiments, I cared about varying the eruption rate. I didn't want to erupt a constant eruption rate. I wanted to see what happens if it changes across different stages of the eruption, like in that first video. And so then I was able to create these things, right? So one of the things I was able to create were these propagation curves, right? Where this is area as a function of time. And you can see this is a 3-stage eruption. And we can see how the area of our flow, each one of these curves is one experiment. We can see how the area of our flow is changing with time. So we can see, for example, in experiment 10, it was increasing at some amount. And then during the second stage of the eruption, the expansion rate increased dramatically. And then it slowed in the third stage. That's because these experiments were erupted underneath a peak condition. We temporarily elevated the eruption rate. And so it was a single eruption, but it had multiple stages of different eruption rates. So this is an example of something you can do, right? Without getting, I won't make this a GSA talk, but without getting into too much detail, this is something that you could do in the laboratory. And you can color code these by the different emplacement modes we talked about earlier. So you can see our green curves here, they had inflation. So those were flows where, yeah, the flow still expanded somewhat, right? But those flows also thickened as well. So those flows did have some inflation, right? Theoretically, they did not get to their full expansion size because some of that material went towards thickening the flow. So it gets complicated, right? You can have these processes happening in parallel also. So this is an example of some of the kinds of data that you can get from these experiments. Okay, fine. What are the implications of these? So here's another one of our wax flows. This one is inflated. This flow has thickened, right? It looks bulbous and smooth because it has inflated and thickened. So why do we care? What's the implication for this? Well, the implication has to do with these experiments in particular. It has to do with our numerical models. So people always ask, why can't we just model lava flows? We have supercomputers. Well, lava flows are extremely complex. They are not solid, they are not liquid, they are not gas. They're all 3, and they're changing as a function of distance and time. So if you try to model that, you can't. It's extremely hard. But we have a lot of different models, and the cool thing about these experiments is that within our models, we have a lot of tunable parameters, and these experiments can inform these parameters. So this is an example of a code called Mr. Lavaloba, which was developed by some volcanologists over at the University of Pisa in Italy. And so this is just a probabilistic model. This is not a fluid dynamics or any kind of like physics in a model. It's literally just a probability-based model, and you feed in topography and things like that and just say, hey, where do you think it's going to go? And so they have a parameter in there called the lobe exponent. And the lobe exponent is simply a parameter that asks, will the daughter lobe become the parent lobe? So each lobe I produce, what are the chances of that lobe producing the next lobe? Or is it just going to be randomly generated somewhere else, right? And so 0 means, oh, it's absolutely going to be each daughter lobe is going to be the parent of the next lobe. So it looks like the image at the top, A, right? So here you have a very thin channelized flow, maybe going down a steep slope. Each lobe makes the next lobe, makes the next lobe, makes the next lobe, makes the next lobe. That's number 0. Number 1, if you have a number that's closer to 1, that means it's going to be random. So now you're going to get thicker flows or wider flows because any lobe can be the parent of the next lobe. So for that, right, what we found is that, well, if you have a strong crust, you have a low psi value, and you have variable eruption rates, your lobe exponent should be closer to 1. So if I know the conditions of an actual lava flow that's erupting on Mount Etna or someplace like that, and I know it has a strong crust, I know the conditions of it, maybe in this model I want a lobe exponent that's closer to 1, right? I'm probably going to need some more data, but it should be closer to 1. If I have a weak crust flow, if I have a channelized lava flow like we saw in that video earlier, maybe my lobe exponent needs to be closer to 0 because I have a weak crust. I'm going to create a flow that's going to be thinner, right? Maybe thinner in height, but also just maybe narrower, right? And it's going to kind of propagate down the slope of our volcano. Maybe. So these experiments do have implications for our numerical models that people use for hazards mitigation and for lava flow forecasting and things like that. We can actually dial into some of these parameters and say, okay, under these conditions, here's what we need. Okay, so that's kind of some of the experiments that I do. There's some other experiments that I'm not going to talk about today where we can actually melt lava. We can just make lava at Syracuse University and University of Buffalo. You can just melt down gravel and actually pour lava and measure it directly with cameras and things. That's some stuff I did a month ago with some colleagues over at University of Syracuse or Syracuse University. And so there are a lot of different ways that you can tackle this in a laboratory where you have some controls. Okay, cool. Now let's switch to extraterrestrial services because now we know, okay, we know how volcanoes operate on Earth. We know we can do stuff in the laboratory, okay? So can we apply any of that to these other planetary surfaces and learn something interesting? So this is an image. This is Mars in the infrared. And this is a volcanic channel on Mars that last I calculated was something over 350 kilometers. It's ridiculously long, 200 miles or so, right? So we see a lot of these volcanic features on our planet. So I told you before that volcanism has occurred on every single planetary surface in the solar system because it is a fundamental geologic process. It's just physics. It's really just physics. I hate to admit it, but the physicists are right. It's just physics, right? So these planets, these bodies have to cool off, so you're going to get volcanism. But Sean, how do we know? Mercury. Here's Mercury, covered in volcanoes. Everything pink is volcanic deposits on Mercury. All right. So the majority of the Mercurian surface is covered in volcanism. This is data that we got from the MESSENGER mission that NASA sent to Mercury back in 2011 and orbited the planet for a couple of years. All right. And so here you have this beautiful image of Mercury, and in everything in pink, these are all volcanic deposits. So we see lots and lots of evidence of lava flows covering the surface of Mercury. Again, not surprising. Mercury is a planet, and presumably at some point it needed to cool off. And up in the upper left-hand corner, you have a topographic image where warm colors are high elevation, cool colors are low elevation. And you see at the northern poles, you have all these huge low elevation area that's just covered in lava flows, right? We have spectral data, we have visible data. So we see volcanism on Mercury. Okay, what about Venus? Covered in volcanoes, all right? So most of us recognize Venus with its clouds on. But here in this left image, this is a radar image looking through those clouds that has been colorized for topography. Cool colors are low elevation, warm colors are high elevation. If Venus looks absolutely scarred and screwed up to you, good, because it is, and we don't understand it, and it is bananas, and that's why we're sending 2 NASA missions back there in the coming years. But if you look at this map here from Hahn and Byrne 2023, what you find is that Venus is also covered in volcanoes. So they've mapped out every single volcano on the surface that's greater than, certain number of kilometers in diameter. And they found hundreds of thousands of volcanoes. 90% of Venus's surface is covered in volcanoes and or volcanic deposits, right? Not only is the planet 900 degrees Fahrenheit on the surface and covered by, carbon dioxide clouds that are suffocating, it's also a hellish volcanic world. All right, Venus is not somewhere you want to go, and it's very, very hard to study because of those conditions. The pressures on the surface of Venus are somewhere akin to what the pressures on Earth are at like 1,000 feet underneath the ocean, right? This is an inhospitable planet, and the only landers we've ever sent there that have survived were the Soviets. Of course, the Soviets built nice, sturdy landers that survived all of 3.5 hours. so Venus is absolutely hellish, but it's covered in volcanoes, covered in lava flows, a rich area for future students to, if you want to go to grad school and study these things. There's a lot of outstanding questions with Venus and with Mercury. What about our moon? Our moon is covered in volcanic deposits. So when you see the moon at night and you see those dark deposits, those dark spots, the man in the moon, the rabbit in the moon, that's all lava. That's all it is, right? Everything on the near side, so the moon has now been stretched out, right? On a Mercator projection or whatever you call it. And so up in the left-hand corner, we have the near side of the moon, what you see at night. All those dark things you see, all of that, those are all lava flows. Those are all lavas which have filled these enormous impact basins from giant impacts 4 billion years ago, right? These lavas are old. I mean, these are 3+ billion-year-old lavas, but all of that is lava, right? So we have Apollo samples. We have spectral data from our instruments orbiting these. These are all just basically basaltic lava flows, the same composition as the stuff that we see in Iceland and Hawaii. A little bit more primitive, but pretty much the same composition. All right, so 20% of the surface of the moon is covered in volcanoes and volcanic deposits. Okay, most of that facing us, on the near side facing Earth. What about Mars? So this is Mars. This is, again, colorized topography. Warm colors are high elevation, cool colors are low elevation. This is Mars. The blue is not water, it's just low elevation. The lower elevation areas. 60% of Mars is covered in volcanic deposits, right? So you can kind of see it. Here we have this area with these enormous, this really, really high topography, these really enormous volcanoes. This is Tharsis. Those are all volcanoes and lava flows and lava channels and any number of volcanic features. There's also some volcanoes down here around Hellas, right? And volcanoes up there. So 60% of Mars's surface is covered in volcanoes. And for scale, this basin, Hellas, is about the width of the United States for scale. A huge impact 4 billion years ago. And this huge volcano you see in the upper left-hand corner, Olympus Mons, that is the largest volcano in the solar system. It is about 70,000 feet high and the size of Arizona, okay? So we have these enormous volcanoes on Mars, a smaller planet with lower gravity, admittedly, but we see volcanism all across the surface of Mars along with other processes. So when we're thinking about our motivation here, right, why do we do planetary geology other than transferable skills and marketable skills and just the cool factor of doing science? It's because volcanism offers a window into planetary formation and planetary interior, right? When these planets belch out material, that tells us about what's going on in the inside of the planet. We know a lot about the Earth's interior because of the rocks that we have at the surface from volcanoes, as well as geophysical techniques and things like that, seismology, all right? But Earth is just one data point. It's one point of reference. So I'm a volcanologist. If I say, hey, I'm a volcanologist and I only understand volcanoes on Earth, I have a very, very limited insight into what volcanoes are capable of. Because there's things that we see on these other planets, which I'll show in a minute, that we don't have on Earth, right? And we also want to think about how we can use existing methods, physical volcanology and experimental tools to investigate other planetary surfaces. Again, this is something that we think a lot about, is how can we use the tools that we already have, the methods and the things that we see on Earth to investigate these other planets, okay? And I just want to make sure I point out here, I mean, we are in a second golden age of planetary science. I did not put on my NASA hat for this talk, right? But there are so many missions currently active in the solar system that I think the public is woefully unaware of. We are in a second golden age of planetary science. There are dozens of missions in orbit around the Earth. There are dozens of missions orbiting the sun right now. If you're a heliophysicist, there are so many missions going on Mars right now. This is a huge concerted effort, and we are going back to the moon in 2 years, right? We're putting people back on the moon in 2 years. We just did Artemis 1 last year. Artemis 2 is coming up. So this is a huge opportunity for students and for early career scientists to really get out there and learn some transferable and marketable skills if you decide to go into the public sector industry, but also to do some really cool science. Even if you studied planets for only a year or two, it's still a luxury and a privilege. So in some previous work, I have done that. And so here, for example, this was work I published in 2017. This is Olympus Mons. This is our volcano that's the size of Arizona. It's 70,000 feet high. It's a shield volcano. It's just like the Big Island of Hawaii, but on steroids. That's all it is. If you zoom in really closely, you just see nothing but overlapping lava flows. It's just even down to the highest resolution data. So on Mars, we're fortunate. We have the entire planet covered at about 5 meters per pixel. About 40% of it is covered at less than a meter per pixel. The moon, we have the entire surface covered at less than a meter per pixel. Has to be. Moon has 5G also. We did that too, because we're sending astronauts back. So we have to have high resolution images. But because we have these high resolution images, we can now do science at really, really small scales. So that lava flow channel you saw earlier erupting in Hawaii, this is an example of a fissure vent just like that on Olympus Mons. You had this fissure that presumably erupted these lavas long ago. And so what I was able to do is I was able to go and look at all these small scale features and map them out and do some science, woohoo, and do some spatial distributions, characterize these to get an idea of the evolution of Olympus Mons in recent Martian history. Right? So this is some stuff that I did when I was a graduate student for like my master's work. But I've also looked at lava flows proper. So this is Tharsis. We kind of blew up that volcanic province we looked at earlier. We have Olympus Mons in the upper left-hand corner, size of Arizona for scale. We have these other shield volcanoes, which are absolutely enormous. And we have this huge volcanic rise. And so these stars represent the locations of some 40 lava flows where I went and looked at characterize these lava flows, right? Widths, depths, morphology. So this is what we see on Mars and a lot of these volcanic provinces. You just see innumerable lava flows overlapping each other, right? And one of the cool things is, if you know a little bit of fluid dynamics and if you make some creative assumptions, right, you can use your topographic data, which we have for Mars. You can use these images. You can use your compositional data, which we have in some places. And you can basically characterize these lava flows, measure these dimensions, plug them into these fluid dynamics equations, and you can calculate effusion rates. You can calculate viscosities with some error bars. You can calculate effusion rates with some error bars and some assumptions. You can calculate emplacement times. What were the conditions of these flows? Okay, are they operating under similar conditions as Earth, right? Are they flowing at the same rates? Are they the same lengths? Are they the same widths? Are they thicker? Are they shorter? What kind of questions can we start to ask with this data, all right? So for this study, I kind of use that thing that I talked about with our experiments earlier. I use our psi value, right? I know that relates morphology to cooling conditions. So I was able to categorize these flows based on their psi value, right? So I have a channelized lava flow. That's a high psi value. Got my levees, got my channel, okay. I have a flow here that has a bunch of compression ridges on it. We see a flow just like this in Arizona, the SP crater lava flow. It's got all these compression ridges on it. It's got a thick crust on top of it when it was in place. Intermediate psi value, getting a little bit stronger. And then we have these lava ridges on like Olympus Mons that these arrows are delineating. This is like a topographic rise, right? That's even a lower psi value. That's a strong crust. Maybe that's Pahoehoe lava. Maybe those are some lava tubes that have been constructed over time or something like that. So you have a strong crustal dominated environment. So each of these scale bars is 5 kilometers, by the way. But so we have these, we can apply this psi value that we use in the laboratory because it is, empirically derived from fluid dynamics, yada, yada, yada. We can apply this psi value to different flows, not just lava flows, but even wax flows. And we can know the conditions under which they were emplaced from that. Now, of course, for Mars, we have to make some assumptions. If you're trying to back calculate psi value to something meaningful, you have to assume some things about the Martian environment. But we got that data too, a little bit from rovers and things like that. So in this study, one of the things I used was psi value, but then I also had to go and do some fluid dynamics. So I used some, fancy equations. And what we found, right, Orange X's and purple crosses is what we care about. What we found was that Mars lava flows have very similar fusion rates to terrestrial lava flows. They erupt at about the same rate, but they're much longer. They are huge compared to Hawaiian lava flows that we have in recorded history, right? And they erupted for longer periods of times, if we assume a constant eruption rate, than our Earth counterparts, our terrestrial counterparts. And they also have much larger volumes, right? These flows are 2, 3, 4, 500 kilometers long. They're 10, 20, 30, 40, 50 meters thick. That's a lot of material. And that's just what we see at the surface. They've been buried by other flows, right? So these are minimal. These are minimum estimates, okay? So what we find on Mars is that the lava flows are a lot longer and they're a lot thicker and they erupt a lot more material. This is a really volcanically active world and we see eruption conditions under which we do not currently observe on the Earth. Do we observe unique landforms on other planets? So here's an example of one of those shield volcanoes. And you can see all these weird little squiggly little tadpole looking things. Those are all lava channels. But those are not constructional features. Those are destructional features. That is carved, we think, into the landscape. There are no levees. We don't see that on Earth. We do not see lava carving into the landscape, but we see it a lot on the moon. We see it on Venus and we see it on Mars and Mercury. It's really, really weird. And so one of the questions that, cheesy photo of me in Iceland, one of the questions that my students, Kijani and Will, are looking at is what causes channels versus channelized flow? So here's an example of one of these lava channels on Mars, scale bar 75 kilometers looking north. And so we have this channel that looks carved into the landscape. We call these sinuous channels on Mars. And here it looks like it's emanating from some subcircular vent. This is me standing near a fissure vent in Iceland last summer where the Krafla lava flow erupted. So this is what it looks like. You saw that kind of video earlier where we saw the lava flow erupting through the channel. Well, once all that lava's drained out and everything's cooled off, this is what it looks like. Back there is the vent. That's where the lava was shooting out 30 years ago, fire fountaining. And this, where I'm standing, would have been the center of the channel. Okay, you had this huge, deep channel. Again, Iceland, just absolutely mind-blowing. And so this region here is probably a good proxy for what was going on here. You had this material erupting out. But on Earth, we have constructional channels. We build things. We make levees. This channel does not have levees. It's just carved into how does lava erode? That's so weird. Water can do it, but lava is a lot different. So under what conditions do we see this going on? So this is an example of one of those landforms I talked about that we don't see on the Earth, but we do see on other planets. Maybe we had them here a long time ago, but they're gone, okay? So this is an active area of research, and I have some students who are working on this, and they're really excited. They're getting a chance to learn GIS and stuff like that, and learn some transferable skills that can be applied in any number of sectors in industry. Okay, so to wrap up, we see volcanoes all over the solar system. This is a fundamental geologic process, okay? It is one of the 4 fundamental geologic processes that act in the solar system. It's just simple physics. Planets and physical bodies have to cool off, so you get volcanoes, you get material being advected to the surface of the planet, and that works to cool them off. When we go out, when we go into the laboratory, we can simulate some of these things, right? We can simulate these lava flows using wax. We can simulate explosion, eruption plumes. We can simulate all kind of crap, dike emplacement, seal emplacement, all these different subsurface processes, all the different things that volcanoes do. We can do a lot of this in the laboratory. We can also do a lot of this with numerical modeling as well, with some simplifying assumptions. And then we can take that work and we can apply it to other planetary surfaces as well. I have horribly condensed 3 disciplines into a 50-minute talk. So I've left out a tremendous amount of detail and information. It's almost criminal, right? I could almost be arrested for how much I've left out. But that's okay. It's a high-level talk. So thank you. I'm happy to take any questions. You can find me on Blue Sky or the other place, which can't be mentioned. And you can also email me if you want to chit-chat here. This is my institutional email. And thank you so much for your attention. I'm happy to take any questions or seditious thoughts. Thank you. And this is the San Francisco volcanic field just north of Flagstaff, Arizona. So for geographical reference. Yeah.
What was your take on the Tonga volcano that just went off in 2022, and it's spewing the amount of water vapor past our atmosphere and messing with our protection.
Yeah. Yeah, volcanoes can do that. So I think the Tonga eruption, I think was like we have an explosivity scale that goes from like 0 to 8. I think it was like a 5 or a 6 or something like that. That was a huge, what we call Plinian eruption. It was a huge plume of material, definitely went into the stratosphere, maybe into the mesosphere. Because it is near the equator, we are concerned about that because volcanoes that erupt on the equator and volcanoes that erupt a lot on the equator can absolutely impact climate for at least a couple of years. They can throw a bunch of aerosols in there. They can mess with ozone. They can mess with cooling the planet. That is literally one of the reasons why we have skating and curling is because a volcano erupted in 1815 and dropped global temperatures and froze the Thames in Europe. And people in Europe are like, I got nothing else to do. Mary Shelley wrote Frankenstein. Lord Byron wrote Dracula, So volcanoes can have socio-cultural impacts, but yeah, they can absolutely go up into the atmosphere and affect the climate. When Pinatubo erupted in 1992, it temporarily halted global warming for 3 years, right? Of course, then it started back up. It's a short time period. It's not, but yeah, they can absolutely have those impacts. Yes.
Well, with atmospheres, are volcanoes essential for creating atmospheres? Like, specifically to other planets?
That's a good question. We think, yes. So we think that, right, at least the immediate, well, I'm going to sort of kind of lie, but I'm going to tell the truth, but I'm going to kind of lie. We think that, yes, that's an essential process. When these planets are forming and they're degassing, right, early age, you have a lot of this volcanism, you absolutely get an atmosphere being contributed that way. The reason I was hesitating was because when the Earth formed, we had a primary atmosphere, which was formed from the actual gas disk. So we initially had like a hydrogen-helium atmosphere. Then that got blasted off by the sun, and then the volcanoes reintroduced this atmosphere. And it wasn't this atmosphere, life made this atmosphere, right? So volcanoes made life change the composition of the atmosphere, I should say. So we do think that volcanoes are essential to the creation of atmospheres. Whether it's a primary or a secondary atmosphere, and the composition of that atmosphere can change with time. So when our atmosphere was formed by volcanoes after our first atmosphere was gone and we had our new atmosphere, there was not a lot of oxygen in it, right? It was mostly nitrogen and a bunch of other volcanic gases, carbon dioxide. When life formed, that's when the oxygen happened, and that's when the composition started to change, and you see that recorded in the rock record. So, but yeah, we do think they're essential for the formation of atmospheres, for sure. Because most of the stuff that volcanoes are belching out is water, carbon dioxide, sulfuric dioxide, things like that, or sulfur dioxide, sulfuric acid. Yeah, good question. Mm-hmm. Essential to planetary evolution, yes.
What did you say your research question was?
I'm sorry?
What did you say your research question was?
Oh, yeah. So I intentionally didn't want to dive so deep. So my research question was, how do variable eruption rates affect lava flow propagation? That was my research question, was how does the eruption rate at the vent of the volcano, how does that actually affect how a lava flow propagates, whether or not it's going to widen, or whether or not it's going to thicken, or whether or not it's going to expand? So how do variable eruption rates impact lava flow propagation? That was my research question for the wax that I showed, those experiments. Yeah, good question. Oh, yeah.
Go ahead.
No, yes, I can wait.
So, speaking of those simulations, you can answer, very specific questions, right? So you sort of set the stage of what you're looking for.
Yeah.
Is it possible or already happening, or do you envision that you could create these models with the topography of certain volcanoes to try to help determine, like, okay, if there's an eruption at this volcano with this current topography, can we predict those directions, or you know what I mean?
No, I know exactly what.
I don't know the scientific term.
No. That was all science. So let me think. So that is being done mostly in the numerical modeling sphere. So people have high resolution digital elevation models of a volcano. They can use LiDAR, or they can get DEM data from airplanes or whatever. They put it in a numerical model. They look at where historical lava flows have propagated. They plug it into their model and say, well, we think it's going to follow this path of steepest topography. We know that there's a topographic barrier here. There's a dam or something like that. A lot of that is modeling. With these laboratory experiments, we have done very simplistic designs of we have put these wax flows on a slope. We have varied the slope. We have put up topographic barriers. We have put slope breaks. We have changed the eruption rate. We've done all that in order to answer these specific questions about these things that we see in nature. So you can do that. I think the experiments are moving into a more dynamic realm. I was reading a paper recently that was like they basically were dripping wax to make these huge volcanic mountains to like make a cone and see like how is that gonna. So people are starting to get super creative with different solutions. You don't even need wax. People are doing experiments with like corn syrup and stuff, right? You can do a lot of these really, really cool experiments. But yeah, in terms of being able to model a specific volcano, that is mostly in the numerical realm. And I think it's just because it's the ease of access of getting that data. They already have that data. And on those volcanoes, especially where you have steep topography, you kind of know where the lava flow is going to go. If you have shallow topography, like in Hawaii around Kilauea, they have so much data because Hawaii has been erupting so long that they can tell based on where the eruption occurs on the island or on the volcano. They basically know with some statistical probability of where the lava flow is likely to go. Oh, it erupted here. Oh, 60% chance it's going to go to the northwest. No worry, we ain't got to worry about that, right? That's actually what they did last December. They saw that it was headed in a particular direction. They were like, oh, this isn't going to threaten any towns, but it might threaten the highway, so we'll keep an eye on it, right? So yeah, a lot of that is in the realm of numerical modeling mostly, but the experiments are starting to get more advanced with respect to looking at morphology and topography and the evolution of volcanoes. Yeah.
Can we influence and maybe even manipulate volcanoes and like eruptions?
Well, you know, should humans manipulate things? Should we nuke hurricanes? We have tried to divert lava flows specifically. Now, should we manipulate volcanoes? That is a social, cultural question. As a geologist, I can say that you are playing with forces that are tremendously more powerful than anything we're capable of. What we have tried to do on the more day-to-day, or I should say on the smaller scale, is we've tried to divert lava flows. So 50 years ago, Iceland successfully pumped 10 billion gallons of water at a lava flow that was threatening to close off a harbor in Hamea, Iceland, a little island that was just to the south of Iceland. They successfully halted that it was something like 50 to 100 feet thick. They successfully halted that lava flow and stopped it. Until you do the physics, which shows that the lava flow was probably going to stop anyway, right? So they hail it as a success. They're thinking about doing this if it erupts in Grindavik in the coming days or weeks. They're thinking about using seawater again to stop the lava flow. It's really, really hard to do. That lava flow is so huge. It's molten rock. You can spray it with water. It's just going to inflate and break out somewhere else. Okay. In the 1930s, the United States, and this is going to come as no surprise, bombed lava flows in Hawaii as a way to divert them. So in the 1930s, they had a lava flow that was threatening Hilo, Hawaii. So they started to drop bombs. The idea was if we drop bombs in a linear fashion, we create this channel, kind of like Volcano, again, 1990s, y'all got to go watch it. We create this like little false channel and then the lava flow goes down this channel and gets diverted. The military claims it was a stunning success. You look at the geology and it's like, it probably was not going to be a problem, right? It's really, really hard. And in Hawaii, you have a large indigenous population that is fundamentally against the diversionary efforts to divert lava flows. They view it as an affront to their ancestor and goddess Pele. And so if you can go on YouTube and watch these really amazing town halls where you have a geologist standing next to politicians and the public is asking that very question, can we divert this lava flow? I know you can do it. And I'm like, not really. And then the politicians are like, well, we're going to do it. And then you have half the room going, well, we can't do it. That is blasphemous, or that is not okay, or whatever. It's really, really difficult. Volcanoes are very powerful. There are small things that we can do to absolutely divert lava flows or to mitigate things, to mitigate volcanic hazards. We can mitigate lahars, for example, mud flows that come off of like Mount St. Helens and Mount Rainier, things like that. Japan and other countries have engineered around that so that those secondary hazards are less problematic so that you can control the flow coming from this melted ice and snow and all this mud. There are ways to engineer a little bit behind it, but when you're talking about enormous volcanoes, I mean,
I was thinking Mars.
I see. Yeah. Oh, okay. I was thinking like geothermal. I was like, oh, geothermal power is great. Iceland has really cheap power because they have a bunch of geothermal plants. For Mars and atmospheres, that's tricky. I mean, I've read Mars, and I know that's one of the things they did in that novel. But you set off a volcano, you don't know what you're gonna get, and we also don't even know if we can do it. These are huge beasts. We're dealing with forces that we still don't quite understand. Theoretically, if we're ever a type 1 or type 2 civilization, we can do this. But yeah, it's really, really tricky. Right now, we mostly focus on hazards mitigation and things like that. But yeah, it's really tricky, but it is really fun thought exercise. Yeah, you're welcome. I love questions like that.
I'm sure you get this question a lot, but Yellowstone being 800,000 years overdue or something like that?
Yes.
Is that what I heard? Is it going to blow or is it just inactive?
So that is a fantastic question, and actually a good friend of mine in grad school was one of the people who did the geochronology who updated that time scale. So I can report to you that we are not overdue actually for a major volcanic eruption at Yellowstone. What's happening is the last massive eruption that blanketed half the United States was 600,000 years ago. That is true. Most of the volcanic eruptions at Yellowstone are just little small lava flows. It's usually nothing bad. In terms of super volcano eruptions, I would actually be more worried about Campi Fieri, which is acting up in Italy right now and causing a lot of seismic activity. For those of you who do not know, the Italian government is thinking about evacuating 50,000 people because there's been all this seismic activity, and there's now been all this data in the Mediterranean where, oh crap, we see all these huge volcanic deposits underwater. Is this super volcano acting up? That's a problem for Italy. Okay, get it, that's bad. In terms of Yellowstone, however, there is no indication that we are overdue for a super volcano eruption. We still may be several 100,000 years away from something like that. We could have a smaller volcanic eruption at any time, and that's probably what's gonna happen. We know that magma chamber, it's not dead. That magma chamber is active, there is inflation, there is magma, that hot spot is still very much active. But chances are you're gonna get just a small, little, tiny eruption. But in truth, we don't really know what a supervolcano eruption looks like. There has not been one on Earth in 70,000 years, which we were around and it affected us, but whatever. But we haven't seen one firsthand, but we know that there would be some indication that something's going on. So right now, I would not worry about Yellowstone. I would worry about some of those other equatorial volcanoes in terms of more shorter term climatic, again, if you have a volcano like Hunga Tonga, if you have a volcano like Hunga Tonga go off again next year or slightly more powerful, then yeah, you could be talking about global crop failures for 2 years, and driving instabilities, climate, impacts, and socio-political impacts, things like that. So that's what I would worry more about, is these smaller volcanoes that can still do a lot of damage and disrupt our lives on some shorter time scale. Yellowstone, wouldn't worry about it at all, wouldn't lose any sleep over it. And if it does erupt, you still shouldn't lose any sleep over it because there's nothing you can do. But also we're in Vermont, so we're not gonna get any ash. So Vermont's fine. We're gonna be okay. Okay. Yeah. Any other questions? Challenges. Fight clubs. Seditious thoughts. Thank you so much.